Okay, so last week we did the representation. Okay. So the basic idea for all this power series representation is this function, 1 over 1 minus x. Okay. So from this function, we can manipulate several other functions that we can find that it has some correlation. It can be manipulate the form, and then we can take out this form from this one. And then we can force the functions to be in a power series. Maybe to give a fresh idea, maybe I will give more example on how we can have the representations. Okay. So if we have x cubed, x cubed over x plus 2. So we want to have this as a representation of power series. Okay. Since we have 1 over x plus 2, like from the previous questions, like last week, we already made the series for x plus 2. So we may take the x cubed to be factored out, and then we can exchange 1 over x plus 2 by the series. Okay, so that's one way we can think. Okay. So we can simply, maybe let me write. So simply we can separate this and then take this into two equations like that, and exchange the 1 over x plus 2. This becomes this sum. And then we can simply just multiply the x. Okay. We can simply multiply the x. And that's it. Okay. Or sometimes the series can have more variations, depends on how you treat the series. For example, if you don't want to have plus 3 here, so maybe we can exchange the form, and maybe we can start from n equal 3. It always shows up because the disk is full, but I've already emptied the bin, but not sure why it's so happened many times. Okay, so we can have the sum from n equal 3, for example, if you like, and maybe because this is 3, so maybe we have to make it into an even number for n minus 1, and then this one will be x with power of n, and we can have this as n minus 2 to make it equal 1. So we can represent the functions x cubed over x plus 2 as a sum of this power series. Okay. Okay, so the idea is based on how we can simplify this, and we can take out the 1 over x plus 2, and we can relate to the base function, which is 1 over 1 minus x. Okay. Okay. Okay, so the next sections, this will be more. It's still representation, but it will be more a little bit complicated because we are using the derivatives and integrations. Okay, let me write the theorem. If the power series So let me write the general form of the power series expansion. Okay. And we say that f is differentiable and therefore continues on the interval, and then we can say that the f prime x, if we derive the function f, this will become c1 plus 2c2 plus 3c3 and so on. Okay. And equal, we can derive the sum. This is n, cn, and then x minus a power of n minus 1. Okay. And then because we can differentiate, we can also think if we can integral. So integrate the f of x. So by integrating, we will plus another constant. Okay, so let me write another constant, just capital C. And then plus C0, we will add x minus a. And then plus C1, x minus a, we increase the power and divide by 2. And this is also increasing the power, become cube. So this is equal to C plus the sum. Okay, so here it is. Okay. And both of this form, it has radius of convergence equal to r. Okay. In terms how we can use the derivative, can write like that for derivative. And for integrations, we can write or let me write in the bottom, maybe here. But regardless of what we have here, the basic idea for the representation function is still the same. We are using 1 over 1 minus x. This differentiation and integration will be related to how we can modify 1 over 1 minus x. So let me just write some notes. Still, the idea is 1 over 1 minus x equal to why it's disappearing. Okay. Okay, please wait for a moment. I need to check my file. All right. Now, from this theorem, okay, let me write that this 1 over 1 minus x, this will be still the key to solve. Okay. So, for example, if we have 1, or maybe we start with the 1 over 1 minus x, and then we derive this. If we derive, this will be resulting 1 over 1 minus x squared, right? Because it has the negative, so it will be multiply with another negative and the positive, right? Or we can think this is minus 1, and then multiply with minus 1, so right. Okay. Do it right here to make sure. This will be minus 1, minus 2, and then multiply with minus 1. So it will be minus, or this will be, right? Okay. Okay. Now, if we can derive this, okay, and if we take the, for example, the expansion of 1 over 1 minus x, 1 plus x, I don't think I need this, plus x squared plus x cubed plus, okay. Now, if we have 1 over, this means we can derive the whole thing, the expansions. So derive, and we can write it as it is 0. So we can start from x is 1 plus 2x plus 3x squared, right? Plus maybe 4x cubed, and then we can also derive the sum. Okay? So we can derive this becomes, this is n, x, n minus 1. And then we can utilize either using derivative or integral. So if we think integral, probably we have the ln form. Okay. Okay, if we observe another example, which is the ln 1 plus x. First, probably we can think on 1 over 1 plus x, which is this is the derivative of so if we take derivative for ln, this will result on 1 over 1 plus x, right? So if we look on 1 over 1 plus x, this will be 1 over 1 minus x. Or we can have this alternate series. Oh, sorry, wrong. And then we need to have our x is less than 1. So this ln 1 plus x is from the integrations of 1 over 1 plus x dx. So we are actually integrating this 1 minus x plus x squared minus x cubed dx. And then it's resulting in, this is x minus x squared over 2 plus x cubed over 3 minus x4 over 4 plus until we have the another new constant. Okay. And we can make out a new series from these expansions. Let's say we can start from n equal 1. And because it's alternate series, we can have negative 1. Okay. And then n minus 1. We start with x with power of n over n. Okay, it's perfectly 1, 2, 3, 4, right? And then plus c. Where from this series we can clearly see x to the power of n, and if we take some time to get into the to check the radius of convergence, this is perfectly 1. Or we can say that we need to have the radius of the convergence is this, and then the radius of convergence is perfectly 1. But maybe before we look on the radius of convergence, maybe we'll look on the constant. Okay, so we need also to configure what is the constant. Okay, so to find the constant, so if we take this, because we have perfectly element of x here, and also we have x here. And if we take x equal to 0 to make it removed from our equations, and we can only look on the constant, then we can try when x is equal to 0. When x equals 0, it's perfectly c is equal to ln 1, which is 0. So we can remove the constant. Okay? So we can remove the constant. So when x is equal to 0, then the ln 1, let me just write 1 plus 0, this is 0 plus c, so c is 0. which conclude that it's true that the ln 1 plus x we can represent as a series of where the x is less than 1, and we can make sure that the radius of matrix convergence then equal to 1. Okay, maybe any questions first? Any questions first? Okay. So what I expect from this representation is from any one of you, if you have any functions that can be manipulated into 1 over 1 minus x. That means we can actually represent those functions into our series. So like the ln, this one, or the previous one, we derived that. And maybe other functions as well. Right? Like for example, the most obvious one is if we have like some 1 over 1 plus something, it should be obvious that it can be represented. Like if you remember 1 over 1 plus x squared. If we can manipulate those functions, we can also relate that into tangent inverse. Okay, so that's also one of the obvious example. So let me go through. F of x is tangent inverse. Let me write. Okay, and if we derive this is perfectly, we have 1 over 1 plus x squared. So we know that this came from 1 over 1 minus x squared. And we can perfectly observe that this is 1 minus x squared plus x4, right? So since the tangent inverse is the integrations from 1 over 1 plus x squared dx, okay? Since this is the integral, then we can integrate this, okay? And we can put it here. So we can integrate. Let me just write this. Maybe let me just copy this. Okay. So this will result in, let me write the constant in the front, plus x minus x cubed plus x5 minus x7 plus dot dot dot. And similarly, we need to find and configure the constant that we get from integrations. So we may check the when x equals 0, then we have tangent inverse of 0, which is 0, and then we have c, and then all other terms will be 0, right? and therefore C is 0. So we can have tangent inverse x minus x cubed or this is similar to, if we look on the series, this will be alternating. It's plus negative. This is odd number, 1, 3, 5, 7, and it's also odd number. Okay. And we can include the odd number pattern or formulations. So we can take this okay. This is tangent inverse x. This is ln1 plus x. Okay, maybe I will give you another example. Okay, maybe giving you an example on if we have f of x find a power series representation for f of x and find r, the radius of convergence. Okay, let me just give you a couple minutes to check. So this should be, we start with if we know how we can find a function, okay, from this particular form, and we remember we can set up maybe differentiation or maybe integration, but perhaps because it has a square, but perhaps we can start for differentiation. So we can start with maybe 1 over 1 plus 4x, and then try to integrate, and try to differentiate, try to derive, and see what is the form. Okay. And then you need to force out to make it into our intended functions, which is has x. Okay. So probably we can start with writing this 1 over 1 plus 4x, okay? And then take this to derive. This will resulting in this bottom will be squared, right? But it will has it has negative, right? So it will be negative 4, okay? Well, it seems the bottom equation is okay, but we have this negative 4. So what we are doing, we can multiply with something to make it to force it to be equal. Okay. So first we can write that this is the intended function. And then we can write, let me write here. This is our results from derivative. Okay. To make it happen, then we can multiply with this. Okay. And then if you want to know this series, we can look on this 1 over minus 4x, or we can have this is with power of n. And if you differentiate, this will be right? Or if you want to write maybe more clear and start from 0, the n start from 0, maybe we can adding plus 1 here and also adding plus 1 so that we have xn. Okay. So we can have this negative x over 4 and then sum of n equals 0. Or maybe we can integrate, multiply x, okay, inside, and 4 with other 4 also. So we will have the sum so this will be 4 with power of n, and then n plus 1, and then x n plus 1. And since the expansions will have negative 4x absolute value, it's less than 1. So the radius of convergence will be 1 over 4, right? Okay. So the difficult thing on the power series and representation is by the representations means that it means that you need to develop or establish the technique on derivative and integration. Sometimes you need to have, if you remember, we have partial fraction. Sometimes we can have partial fraction, and maybe we can integrate each equation and become each series. Sometimes we can also do that. Maybe I will give you maybe one more. Yeah, maybe one more example, and then we can move to the next part, which is the Taylor series and Maclaurin series, which is similar to what we have here, but it's more specific. Okay, let me give you another one. We'll write here. The functions is 1 plus x over 1 minus x squared. So what the question is, finding the power series. Okay, so let's back to the course. Okay, back to the reality. Okay, so similarly for functions 1 plus x over 1 minus x squared, maybe let's go a little back to what we did before. I think wait, maybe here we have this sum, right? So let me just copy this and see if we can take it into our equations here. So this is 1 over 1 minus x squared, right? And to make it more easier to look at and easier to be calculated, let me just take it to n equals 0 and make it into this n plus 1 and an x to the power of n. Okay, and this is just the similar form but different writing. Okay, and then if we look on the functions, we can write the functions in terms of And I hope you can see how we can deal with this. Okay. So whenever you see any function that you can separate and becomes each one is each series, then you can deal with the series, and then later on you can combine it all together with become one full series. Okay. So we can write in this one here 1 over 1 minus x squared. This is precisely this, n plus 1, and then x with power of n. Okay. And then the other one, the same, but we are multiplying the x, so n plus 1, and then x, n plus 1. It seems that we can try to make it into our one sum of the series. Okay. Okay, so we can write and if you look closely, that this is starting from 0 and this is plus 1. If I start from 1, then I can erase this plus 1, right? So we can have started from the same n equals 0, and we can remove the plus 1. Okay, so n and x with power of n. Okay. Sorry, this should be 1. Okay, now we have the same x with power of n, but we have different this 1 and 0. The next technique or the next method that usually we are using is, if we simply look at this left series, if we take 0 to the series, so n equals 0, so 0 plus 1, x with power of 0, so 1, 1, so it's just 1. Okay, so we can write 1 plus so we can write like this. Okay, we can exchange the n, and then we need to extract the other one. Okay, so we extract the 0 and then we make it into 1. So the rest of the series will be plus from n equal 1 for the series. Okay, and because this is n equal 1, we can combine this. Okay, so we can combine. So this means that we can combine plus n plus 1 plus n, and then x with power of n. So we have 1 plus and then if you play with the series here, okay, we have n plus n to n plus 1, and we play the n. Okay, imagine n is 0. What will happen? It's just 1, right? So we can combine also this one. Okay, because 1 is, when n equals 0, it's 1, right? Okay, so we can make out this series as okay, and that's our series. So first we can separate the functions, and each one we can have their own series, and we need to think how to combine all together. And sometimes you need to think on trying some n, maybe 0, 1, and then we need to make it equal. Okay, so we need to make it equal. So we need to make the starting value equal. So that we can, by the end of this calculation, we can combine both series. Okay. So sometimes when you have maybe stuck on what to do, maybe you can try several n. Maybe n0, 1, and see how it looks like. Okay. I think later maybe I will give you more practical things, like maybe exercise. But most of the 11.9 is finished. Okay? So power series we have, and then representation of functions, and then using differentiation, using integration. Okay. Next section will be still similar to what we represent here, how to represent the functions, but they will more specific. Okay, maybe we start with looking at the functions. So this is 11.9. We call this is Taylor and Maclaurin series. Both are mathematicians. One is from England, one is from Scotland. I think it's 1700s, I think. 17th century. Yeah, from 17th century. So first, before we look on the theorem, let's look on the function that we have established, that is C0 plus C1 and this x minus a should be less than the r. So first, we need to determine what is the coefficient, the first coefficient, to make it more easy to imagine. Let us take x equal a. If x is a, so when x is equal a, when x equal a, all the terms that has x minus a will be gone, and we are just left with the coefficient, which means that f of a is equal to this coefficient. Okay. Okay, that's the first one. The next one, in the previous section, we can differentiate the expansion, right? We can differentiate the series, the expansion series, right? So let's try to differentiate. Okay, so let's differentiate the f. So let's write f from x. So this will be C1, or maybe not C1. Oh yeah, C1, because it's x minus a. And we differentiate C2, we have 2C2, right? Plus, then x minus a. And then plus 3C3, x minus a squared plus 4C4, then x minus a cubed plus dot dot dot, and still we have the x minus a should be the radius. Okay, and again we try when x equal a, and we see that our f prime a is C1. Okay. Now, if we differentiate one more time, it becomes interesting. And maybe we differentiate 4 or 5 times, we will see how the coefficients looks like. Okay. So let's try to differentiate one more time. So f double prime, the second derivative. this will result to C2, and this will result to going to the front. Okay, it becomes 6, but I will write still 2 multiplied by 3. Okay, to see the pattern that we have. So 2 multiplied by 3 and C3 x minus a squared, and then we also have 3 multiplied by 4 C4 x minus a squared, and then plus dot dot dot. And still this is the radius. And then the f prime, when we have x equal a, the f double prime now will be 2c2. Okay. Well, maybe it's not. It's still less interested. But if we try the third derivative, okay. This will be 2 multiplied by 3 c3. Oh, I think it should be, okay, should be 1. Okay, sorry. Okay, now 2 multiplied by 3 c3 plus 2 multiplied by 3 multiplied by 4 c4 x minus a. Okay. And then if we have another one, this will be plus 3 4 5 c5 x minus a squared, and then dot dot dot. Okay. And if we have x equal a, for the third derivative, this will equal to multiplied by 3 c3. And if you try to take the fourth derivative, the fifth derivative, you will see that it will be 2, 3, 4, 3, 4, 5, 4, 5, 6, okay, 5, 6, 7, and so on and so on. And we can take that form and write down as, we can write down this is as 3 factorial C3. So if we have f with some degree of differentiations, okay, let me write as n like that, of a, this will equal to multiplied by 3, multiplied by 4, multiplied by 5, dot, 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 up until some n of Cn, or we can write as n factorial of Cn. And the coefficient itself, we can get that this is Fn a divided by n factorial. And this formula is still valid for n equals 0 because 0 factorial is 1, so it's still valid. So you can find the coefficient on your expansion for the functions, for the power series expansions, and then you can find through this how many times you derive. Okay. So if you derive maybe 5, 6, 7, you can just take it at 7 and then 7 factorial. Okay. So maybe let me just let me recap the theorem for the power series. So if F has a power series representation, expansion at A if f of x is some then its coefficient will be equal okay. So if we substitute back to the if we take the Cn and we put here, then we can also write down the functions as, so we can also write the f of a, or maybe start from f of x first and write down the coefficient. And we can write this as f of a, okay, plus f prime a divided by 1 factorial, and then x minus a, and then plus f double prime a x minus a squared 2 factorial, and then increasing into third derivative, and then 3 factorial, and plus dot 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 dot. Now this is called, what this section is about, this is called the Taylor series. So, or we call the Taylor series of the function f at a, or we can call centered at a. Okay, if we remember the power series, the radius of convergence, so it's centered at a. And the functions can be varied. For example, you can have the exponent, some trigonometric that we can have this kind of Taylor series. Because if you remember the sine or cosine, they will have, we derive, it will be only between sine and cosine, right? So we can have sine, cosine. And we will later, we can try some example on how we can deal with the Taylor series. So from playing and finding from the coefficient, we can get a new form that depends on how the functions and its derivative can be represented into a long chain of series. Okay. Now the other series is called the Maclaurin. Essentially, they are the same. There is only slight difference. So basically, if you know how to write down the Taylor series, and I think because it has like special pattern, that if you look, so just f of a, f first derivative, n equal 1, 1 factorial. Second derivative, 2 factorial squared, 2, n equal 2. So 3, so 4, 4, 4, 5, 5, 5, and we can add as many as we want. Okay? So I believe this should be easy to be established by yourself, okay, if you write down the series. Okay. Now, the other series, which called the Maclaurin, okay, the Maclaurin. Maclaurin series is when Taylor series has A equals 0. Okay, so which means that let me copy this Taylor series. So if you see the difference. So you write this is Taylor. Oh, wait. This is Taylor, and this is Maclaurin. So Maclaurin will be when A is 0, so 0, and n factorial, x to the power of n. This will be f0 plus f prime 0 x, and then factorial plus and 3 factorial and plus . If you're wondering, okay, how to write, if you have 4, 5, we can write like this, or 5. Okay, this it's just usually we write 1 to 3 with this like this line. We call it the accent. But if you do more than 3, we can describe it with a number. Okay, so this is called the Maclaurin. So basically it's the same as the Taylor, but the difference, the A is equal to 0. So basically what this two series means, or the Taylor and Maclaurin, okay, if we relate to what we've done in representation of the power series in 11.9 previous section, which means the Maclaurin is, so all the power series representations that we find, that we already developed before, we can actually represent and trying using this series also. Okay. So for example, so we know that the 1 over 1 minus x. This is, if we expand, okay. So we need to confirm whether the series, okay. And you see that because this is, we can imagine if this is the Maclaurin, if this is Maclaurin, A is 0, right? A is 0, and it has certain happening here. So what will happen is we can confirm, okay, the coefficient by giving the okay. So first we compute, and f0 is 1, right? So we compute derive is also 1, right? But then we have second derivative, and we'll see that it's going to have cube at the bottom, and then this will be 1 multiplied by 2, or we can say second derivative at x equals 0 will be 1 multiplied by 2. If we have the third derivative, this will be 1 minus x with 4, and then this will be 1, 2, and 3. Okay. So in general, we have, this is the n factorial, and this will be n plus 1. And then from here we can decide that this is depends on the n. Okay, so it's n factorial. And then remember that the coefficient that we have, this is fn 0 divided by n factorial. This is n factorial divided n factorial, which is 1. Okay, and that is what we have 1 here at the very beginning of the expansion. Okay, and then the 1 over 1 minus x, we can define this in terms of this coefficient multiply with x with power of n. And since this is 1, then this is precisely true that this is x with power of n. Okay? So all the representations that we have in the power series, we can also represent in terms of Taylor and Maclaurin series. And I think for more practicality, the Mclaren series is much more applied. The application for Maclaurin is much more real because it deals with when A is 0. So we are excluding the A. But when we analyze, if something happened, like we want to know more on the convergences, then we need to include A because it has the interval of convergence, right? It has the radius. But when we deal with the Maclaurin, we are excluding the A, so we are much more having much more converged point. So most of the functions that is already established, we can deal with the Maclaurin. Okay. Let me check the other. Okay. Now, if f of x is e with power of x, since we have the when x is equal 0, all the derivative of e will be equal 1. So if we relate to our Cn x with power of n, if we exchange this then this will be 1 plus x 1 factorial plus x squared 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. So e to the x and if you need to find the radius of convergence, we can do the ratio test, okay, if you like. So by ratio test, so let an be xn so we'll have this will be x, and then precisely we have x, absolute value of x, and then limit as n going to be infinity 1 over n plus 1, in which this limit will result in 0, which means that radius of convergence will be infinity. Okay, so the series converge for all x. And interestingly, if you let x equal 1 for e to the x, then you will have e is equal we will get back into E maybe next Thursday, but let me just show you another functions that appears often. Okay. If we start with sine, if we have sine, okay, and then if we need to find the Maclaurin series, okay, we can determine each functions when x equals 0. We derive once, become cosine. So 1. Derive second time, it's become negative sine. And it's 0. And third time will be negative cos x, and this will be negative 1. And maybe fourth time, it's back to the original one, okay, back to the sine. So if you see how we observe this, there's 0, 0, 0. So maybe for sine and cosine, for the even number and an odd number, there will be sometimes we have 0, sometimes it's not. So we can write down the formulations for the Maclaurin. That is maybe here. I will write here. The Maclaurin we have. And since every odd number, F0, or every 0, 2, 4, so every even number will be having a 0. So 0, 0, so we will have on the odd number. Okay? So we can write down the Maclaurin series as x minus, oh sorry, this should be minus. Minus, yeah, right. Minus, this is minus, right? Okay. So minus x cubed and plus x5 and minus x7 and plus, and we can rewrite this as the odd number 2n plus 1. And this becomes 2n plus 1 factorial. So sine x will be equal to for all x. If you want, you can also try to make the cosine x. The cosine x will result in the even number. So if sine has the odd number, cosine will have the even number. So to represent a function as a power series, if we conclude from the previous section, we have 1 over 1 minus x. We have also the ln, 1 plus x. 1 over 1 plus x squared, we derive the 1 minus x. And then we have also the e to the x we did before, sine x, cosine x. And also before we learn also the tangent inverse. So that's also we can represent as a power series. So every functions that we learned before that we can represent, we also can make it into our Maclaurin series. And the conclusion is the same conclusion. Okay, I think I will just stop until here, and we will back to the e to the x. I'll have some more explanation because I think it's really interesting for e. Because if we derive e, it's still e to the x, e to the x, right? Maybe later we'll have much elaboration on these functions. Okay, in the meantime, Is there any question? Is there any question? If there's no questions, then I think I will just stop until here. We still have a little bit sections on the Taylor and Maclaurin, and then the last part is more about applications. So I think it's not really really a lot. So, and I think I will just skip some of them. Just skip a little bit because we are not really dealing with them. So yeah. Okay, I think we can stop here.